Hello, my presentation topic is on mobile cloud computing. This is presented from my cloud computing class for spring 2022 with Professor Calva. First, I'm going to tell you a little bit about me. My name is Joseph Gundel. I currently have a master's in computer engineering, which I received in 2012 from FAU. I currently work as a senior embedded software engineer for Hayward Holdings. I'm currently in the PhD Computer Science Professional Program. This is what I plan on covering in this presentation. I will cover mobile device technology. I'll go over cloud computing versus mobile cloud computing. I'll talk about some mobile cloud computing solutions, some offloading methods, some cost-benefit analysis, some security, and some issues and barriers. Smartphones are becoming more powerful every year. In fact, they are taking the place of normal desktop computers for both work and personal use. Smartphones' hardware technology has improved to perform intensive computing tasks rather than basic computation, such as image processing, face recognition, heavy calculations, and gaming. Currently, the number of smart devices, such as smartphones and tablets, are growing noticeably compared to the computing desktop. Smartphones have now been equipped with features such as cameras, advanced user interfaces, sensors, and powerful processors. These features enable many beneficial applications. Today, one can hardly imagine a day without the support of these multi-purpose phones that have made our lives unbelievably convenient. Even with all the advancements in mobile technology, mobile devices are more constrained compared with desktop computers. Processing capabilities, some smartphones cannot handle heavy tasks such as face recognition and gaming. With memory capacity, rich media needs a massive storage, and smartphones require big storage to cope with massive data. Limited battery energy. Although there were improvements in the smartphone circuits, the battery is still one of the big issues. Smartphones require more energy than what the embedded battery's capacity provide. This is due to processors becoming more powerful and faster, screens are getting larger and more colorful, and devices are provided with more sensors and actuators. There are only slight improvements in the mobile battery functions. The current battery lifetime and the future trends are not predictable. So what is cloud computing? According to the NIST definition, cloud computing is a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources, such as networks, servers, storage applications, and services that can be rapidly provisioned and released with minimal management effort or service provider interaction. No longer are developers and businesses required to deploy and maintain big data centers and computer infrastructure to support their applications and services. They can now pay for utility computing or pay per use. This allows them to scale up and down based on demand. So what is mobile cloud computing? Mobile cloud computing, or MCC, is the combination of cloud computing and mobile computing to bring rich computational resources to mobile users, network operators, as well as cloud computing providers. Mobile cloud computing is defined as an extension of cloud computing with a new ad hoc infrastructure based on a mobile device. Mobile cloud computing was defined on March 5, 2010, in an entry in the Open Gardens blog as the availability of cloud computing services in a mobile ecosystem. This incorporates many elements, including consumer, enterprise, femtocell, transcoding, end-to-end security, home gateways, and mobile broadband-enabled services. So why mobile computing? Information at your fingertips, anywhere, at any time, has been driving vision of mobile cloud computing, so that users can have a better experience to access information and enjoy many applications in the mobile cloud computing environment through mobile devices. There are a lot of applications with mobile cloud computing, such as image processing. Every mobile device now, most of them have cameras. Cloud computing, which video recordings from multiple mobile devices can be spliced to construct a single video that covers the entire event from different angles and perspectives. So, for example, if you're at a concert or some sort of venue and there are multiple people taking videos, they can be combined to create a better user experience for everybody. Also, you can use it, for example, for like if there's a lost child or in disaster relief. Those are more applications for mobile cloud computing where you would need a lot of dynamically changing information real time. Also, sharing GPS and internet data. It is more efficient to share data among a group of mobile devices that are near each other through local area or peer-to-peer networks. It is not only cheaper, but it's also faster. Instead of going through the cloud, you can do peer-to-peer. There's also sensor data application. Since most mobile phones are equipped with sensors, today reading from sensors such as GPS, accelerometer, light sensors, microphones, thermometers, clocks, and compass can be time-stamped and linked with other phone readings. There can be queries executed on this data. So, for example, someone could say, what is the average temperature of nodes within a mile of my location? This can be used for, traffic. If everybody has mobile phones, if they're driving and there's congestion driving, they can use that information from the accelerometer and GPS to figure out if there's like traffic conditions near you. Also, multimedia search. Mobile devices store many types of multimedia content, such as videos, photos, and music. A good example is Shazam is a music identification service for mobile phones that searches for similar songs in a central database. In the context of the mobile cloud, the searching could be executed on the contents of nearby phones. Another big topic is social networking. Since sharing user content is a popular way we interact with friends on social networks such as Facebook, integrating a mobile cloud into social networking infrastructure could open up automatic sharing and peer-to-peer multimedia access. And this will also reduce the need to back up and serve all of this data on huge servers. Okay, so now let's talk about some mobile cloud computing constituents. Mobile cloud computing is made up of a complex network and relationship of and in between infrastructure providers, which is in blue, application service providers, which are in red, and end users and developers, which are connected to the internet to these application service providers. Okay, now I'm going to go over some mobile cloud computer example scenarios. Commonly, the term mobile cloud computing means to run an application such as Google's Gmail for mobile on a remote resource-rich server. In this case, it would be the Google servers, as displayed in this figure here. While the mobile device acts like a thin client connecting over to the remote server through cellular. Some other examples of this type are Facebook's location-aware services, Twitter for mobile. Another example would be like mobile weather widgets. This is what is the commonly known definition for mobile cloud computing. I'd like to introduce another one. This is a peer-to-peer network. With this approach is to consider other mobile devices themselves as resource providers of the cloud, making up a mobile peer-to-peer network as in the figure. The collective resource of the various mobile devices in a local vicinity and other stationary devices too, if available, will be utilized as shown in this picture here. This approach supports user mobility and recognizes the potential of mobile clouds to do collective sensing as well. Peer-to-peer systems such as Satin for mobile self-organized exist, but these are based on component model systems, representing systems made up of interoperable local components rather than offloading jobs to local mobile resources. Is another concept that this is the cloudlet concept, which is another approach to mobile cloud computing. This illustrates where the mobile device offloads its workload to a local cloudlet comprised of several multi-core computers with connectivity to the remote cloud servers. Plug-in computers can be considered good candidates for the cloudlet servers. I think specifically the low footprint and small form factor computers would be used with lower power consumption. These cloudlets would be situated in common areas such as coffee shops and libraries and like universities, so that mobile devices connect and function as a thin client to the cloudlet as opposed to a remote cloud server, which would present latency and bandwidth issues. So basically, the local cloudlet will connect with usually like a hard line to the remote cloud, and your mobile devices would connect to this local cloudlet. Okay. There are several methods which provide solutions for mobile cloud computing, and we generally categorize them into two families. We have general purpose mobile cloud computing, or GPMCC, and application specific mobile cloud computing, ASMCC. Both of them have advantages and disadvantages and are not mutually exclusive. In general purpose mobile cloud computing, a general system is constructed which uses the cloud infrastructure to help improve mobile device performance. In this article down here, Augmented Smartphone Applications to Execution, they introduced the idea of improving the performance of hardware-limited smartphones by using their proposed clone cloud architecture. They created virtual clones of the smartphone, execution environment, and cloud. So basically, they have a virtual smartphone in the cloud, and they transfer tasks execution to those virtual devices. So they offload execution from the smartphone to a computational infrastructure hosting a cloud of smartphone clones. In case the smartphone is ever lost or damaged, the clone can also be used as a backup. Another advantage is that hardware limitation of the smartphone is overcome. Task is transferred to high computational devices in the cloud. It also makes the developer's job easy, as there's no or few modifications needed to their application. Because their application is running on a virtual device, which is supposed to be the same architecture, they don't really need to modify their application. I missed this one. So in application-specific mobile cloud computing, specific applications are developed for mobile devices which employs cloud computing. Applications such as email or chatting needs ASMCC. This is because internet is used as a communication resource and not only for storage or additional computational power. ASMCC has the ability to make mobile devices a more powerful computing device and provide use of many applications. In this mobile service clouds paper I found, they introduced service clouds for mobile cloud computing and named it mobile service clouds. Their model enables dynamic instantiation, composition, its configuration and reconfiguration of services to be used by the mobile user. In this Secure and Elastic Applications article, they created elastic applications which augmented smartphones utilizing elastic computing resources from the cloud. An elastic application could have one or more weblets in it. The weblets of single application can communicate independently or with other weblets. Weblets can be exchanged between mobile devices and the cloud. Their approach also provides a solution for authentication, secure session management, secure migration between weblets running mobile devices and those on the cloud. Jason Christensen, in this article, using RESTful web services, propose a method for creating mobile applications using cloud computing and RESTful web services. RESTful web services are much more simpler and easy to use. The main goal is to offload computational capacity, storage, and security of the mobile devices to cloud by utilizing the RESTful web services. All right, so now we're going to talk about the actual offloading methods. The main operation in any mobile cloud would be the offloading of jobs that take place from the resource-constrained mobile device to the cloud. Because of issues such as physical distance separated the mobile devices in the cloud and the heterogeneity of the underlying systems, different research has tackled this in a variety of ways. Current research discusses offloading methods in three major directions, as you can see here: client-server communication methods, virtualization, and mobile agents. And this diagram from the Mobile Cloud Computing, a survey, is a pretty good diagram. You can see it has some examples of each. So for the client-server communication, it references Spectra and Chroma, and also the Cuckoo and Hyrax technique. Also, the pros is it's stable and well-supported APIs. The cons are it needs prior installation, it's prone to network congestion, and it's not suited for disconnected operation. Whereas virtualization, I think most of the research now is with virtualization and mobile agents. The pros of the virtualization is there's really no code rewriting, and it insulates the server. The cons are VM synthesis takes time, and there's compatibility issues between VM overlays. For mobile agents, dynamic deployment, it's suitable for mobile and disconnected operation. The cons are the security constraints, issues with agent management. All right, so first we're going to talk about the client-server communication. In the client-server communication process, communication is done across the mobile device, the offloader, and the surrogate device via protocols such as remote procedure calls or remote method invocation and sockets. Both RPC and RMI have well-supported APIs and are considered stable. They're stable by developer standards. However, offloading through these two methods means that the service needs to have been pre-installed in the participating devices. This is a kind of a disadvantage when considering the ad hoc and mobile nature of a mobile network, and it restricts the mobility of users if in the vicinity of devices that do not support the needed services. All right, so now I'm going to go over some client-server examples. And these, I got this information from this paper, Mobile Cloud Computing, a survey from Fernando. Spectra and Chroma are two examples of systems that use pre-installed services reachable via RPC to offload computation. Applications use the RPC to invoke functionality in remote and local Spectra service. When the device needs to offload an application, the Spectra client consults a database that stores information about the Spectra servers. Spectra servers, such that their current availability, CPU load, etc. These servers are pre-installed with application code acting as services. Developers need to manually partition the application by specifying which methods might be candidates for offloading. It's actually one of the drawbacks of the system. Spectra decides at runtime, depending on the resource pool, which of those aforementioned methods, if any, will be offloaded and to which surrogate. Hyrax for Android is only for Android smartphone applications, which are distributed both in terms of the data and computational based on Hadoop, which was ported to the Android platform. Hyrax explores the possibility of using a cluster of mobile phones as resource providers and shows the feasibility of such a mobile cloud. In Hyrax, a central server with access to each mobile device coordinates data and jobs. And the phones communicate with each other on an isolated 802.11g network, just like in the normal Hadoop implementation. So this uses Wi-Fi. Each phone runs threads that stores the phone's multimedia data on the Hadoop distributed file system and threads that record sensor data. So this is all based on Hadoop. The Cuckoo framework presents a system to offload mobile device applications onto a cloud using a Java stub proxy model. It can be offloaded onto any resource that runs the Java virtual machine, be it a commercial cloud, such as Amazon's EC210, or a private mini cloud comprised of laptops and local clusters. Anything that can run a Java virtual machine can be used. The Mobile Message Passing Interface, the MMPI framework, is a mobile version of the standard MPI over Bluetooth, where mobile devices function as fellow resource providers. Instead of the typical star network structure of normal piconets, MMPI employs a fully interconnected mesh structure so that each node can communicate with the other. And that's through Bluetooth. And now we get to some fun ones. Okay, so this is using the virtualization VM migration method. With the exception of Hyrax and Cuckoo, the most recent works have used either VM migration or mobile code to offload tasks. This is where the most recent research is based out of. Trends in this particular area favor VM migration and mobile code over the conventional client-server communication systems. Although client-server communication methods have well-supported APIs and are robust, they require the applications to be pre-installed. Also, disconnected operations are not supported in this method. Considering the ad hoc nature of mobile systems, this is a disadvantage. So, if you don't have internet connection, you can't use any of those other services. Furthermore, the continuous ongoing interaction and communication between the client and the server may lead to network congestion. VM migration is used by a majority of frameworks, including Cloudlets, MAUI, which is the mobile assistance using infrastructure, Clone Cloud, and Mobile Cloud. Virtualization greatly reduces the burden on the programmer, since very little or no rewriting of the application is required. However, full virtualization with automatic partition is unlikely to produce the same fine-grained optimizations as that of hand-coded applications. Although rewriting each and every application for the code offload is also not practical. MAUI actually does not rely on pure VM migration, as done in Clone Cloud and Cloudlets, but uses a combination of VM migration and programmatic partitioning. In cases where the mobile device user is within range of a surrogate device, for a few minutes, using VM migration may prove to be too heavyweight. So if you're only around for a couple minutes, it may not be, and it may not make sense to use that. It's important to analyze the cost of offloading on the cloud. It may not always make sense. So most applications that are going to try to use this need to make a decision if it makes sense to offload. And the cost of offloading on the cloud are, such things as time, energy, and monetary versus monolithic execution and storage. Sometimes it doesn't really make sense to offload, and I think most of the research has been on creating engines that are for creating decision on whether it makes sense to offload or not. So now we're going to go over. Okay, so now we're going to cover some examples of some of these systems and how they do the cost-benefit analysis. Spectra uses a prediction model based on the assumption that a resource consumption of an operation is similar to recent executions of similar operations. In the case of encountering a new operation for which history data does not exist, the model employs linear regression to give an estimate. So basically, on empirical data, it can try to classify and figure out if a task is similar to a previous task, and it creates a model, and then it can put that input into a model and make a decision based on that. Chroma uses a somewhat similar approach called tactics, specified in a declarative language. Chroma also employs resource monitoring and history-based predictions to weigh the outcome of each tactic plan against the estimated cost. History data for applications are logged offline, and predictors update the logs online and use machine learning to optimize the predictions. To come to a decision, Chroma performs a trade-off using utility functions that perform comparisons between attributes such as power consumption and speed. However, unlike Spectra, the adaptive policies are separated from decision-making and policy enforcement at runtime. The scavenger framework also employs a cost assessment method to decide whether offloading should be done or not. This is carried out by the scheduler component, which considers the following, the relative speed and current utilization of the surrogates. A CPU benchmarking method is employed to evaluate the performance of potential surrogate devices. Also, network bandwidth and latency to the surrogates. Network connection information is statically configured to avoid unnecessary traffic. Using this information on expected bandwidth, Scavenger estimates the cost of remote execution. Also, based on task complexity, this does not refer to the big O's asymptotic time. Rather, this means an estimate of how much time it would take to execute the task on the surrogate device. And also on input and output size. Input size is available at runtime, but the programmer needs to specify the information on output size. MAUI carries out a cost-benefit analysis by profiling each method in an application through serialization. Measurements of network bandwidth and latency are also taken into incorporate into the cost. Specifically, MAUI's profiler takes 3 issues into consideration: the device's energy use, application characteristics, and network characterization. An energy profile of the mobile device is prepared by first measuring the battery usage from a hardware power meter. Initially, the profile is trained on the device by collecting data on CPU utilization and energy consumption. These values are used to construct a linear model that is able to estimate how much energy will be consumed by a method. This estimate is given in the form of the number of CPU cycles it requires to execute that particular method. The application characteristics, since profiling an application for each of its possible paths will be expensive, MAUI uses the past invocations of methods to predict the future invocations. And then also network characteristics. They follow a simple procedure to measure network throughput. 10 kilobytes of data is sent to a MAUI server and is observed to obtain an ideal of network bandwidth and latency. Also, the profile records the statistics of network quality every time a method is offloaded, and this history data is utilized for future estimates. CloneCloud employs a dynamic profiler to collect data used in the cost-benefit analysis. That is then fed into the optimization solver to decide which methods need to be migrated. The cost of migration and execution will be minimized. Here, the cost could refer to execution time, energy consumption, or resource footprint. Here's kind of a breakdown. So when the cloud receives a request for migration from a mobile device, it will only accept it if there is an overall system gain. The overall system gain is based on maximizing the cloud profit and reducing the expense of the mobile user. The expense of the mobile user depends on the trade-offs of energy consumption in a mobile device versus the monetary cost of offloading to the cloud. Existing cost models in current mobile cloud computing systems mainly fall into 3 categories: history-based profiling, parametric, and stochastic. And this table here kind of goes over the examples we went over and what category they fit into. For example, Spectre and Chroma are history-based profiling. Scavenger is also history-based. MAUI is history-based. CloneCloud is history-based. And the Kumar and Liu model is parametric. And the other one, Mobile Cloud, is a stochastic method. And you can see the objectives here. So for Spectre and Chroma, it's user-specific, reducing in execution time, energy usage, and increasing fidelity, improved performance and energy saving for Scavenger. And then it also talks about some of the benchmarking. I'm not going to go over this, but you can see it. So now I'm going to kind of go over some of the cloud security concerns. So mobile cloud computing inherits some of the security issues with regular cloud computing. And so according to, these are the 7 cloud computing security risks specified by Brodkin. And he outlines the 7 security risks users need to consider in cloud computing. That includes privileged user access, Offloading sensitive data to the cloud would mean the loss of direct physical, logical, and personal control over the data, right? Regulatory compliance. The cloud service providers should be willing to undergo external audits and security certifications. Data location. The exact physical location of users' data is not transparent, which may lead to confusion on specific jurisdictions and commitments on local privacy requirements. Data segregation. Since cloud data is usually stored in a shared space, it is important each user's data is separated from others with efficient encryption schemes. Recovery. It's imperative that the cloud providers provide proper recovery mechanisms for data and services in case of technological failure or other disasters. Investigative support. Since logging and data from multiple customers may be co-located, inappropriate or illegal activity, should they occur, may be very hard to investigate. And then long-term viability assurance that the user's data would be safe and accessible even if the cloud company itself goes out of business. Those are so that's normal cloud security concerns. Now, in addition to the concerns just listed, securing a mobile cloud introduces the following challenges. Authentication between the weblets that would be distributed between the cloud and the device. Authorization for weblets that could be executed on relatively untrusted cloud environments to access sensitive user data. And establishment and verification of trusted weblet execution cloud nodes. So these are added security concerns. It has to make sense to offload, right? So it has to be energy awareness, especially because mobile devices have limited battery. You have to look at the overall energy cost. And the overall energy cost is the computational energy cost plus the communicational energy. Also, the system energy cost is the overall energy cost plus the overall infrastructure energy cost. Now, it may take more energy to transfer the data through the network medium than it would be to just handle whatever the task is on the local device. So that has to be accounted for. Because a mobile device operates on a finite supply of energy contained in its battery, energy is one of the key resources that needs to be used carefully. In the context of mobile clouds, the cost of participation, such as power consumption, should be less than the benefit gained. So it shouldn't cost more than the benefit you gain from it, right? You don't want to use more power than what you would save. Also, it will enable the mobile device to take appropriate component-level action to minimize unnecessary energy consumption and hence lengthen the system's lifespan by unloading unneeded software components, redeploying energy-intensive components to more resourceful hosts, and co-locating frequently communicated hosts. So here are some barriers and issues with cloud computing. I should say mobile cloud computing. It's actually barriers and issues with mobile cloud computing. I apologize. Mobile cloud computing is an extended branch of cloud computing, so definitely there are some potential issues that appears to be barriers to this ever-changing shift from cloud computing to mobile cloud computing. The cloud is computationally powerful, while the mobile devices have limited computational resources. Some barriers are absence of standards or lack of open standards. Resource poverty. Generally, the mobile devices have less computational power, limited storage capacity, poor display, and battery constraints as compared to the personal computers. This can be solved with offloading computation. Network bandwidth or latency. Another issue is mobile cloud computing is limited bandwidth and high latency of network. Bandwidth for cellular systems may be limited by cell tower bandwidth in some areas. With low power signal reception, it leads to lower bandwidth and higher latency. Wi-Fi is a solution to improve network latency, but if the number of mobile users is too much, then the bandwidth is decreased. The upgrading to 5G wireless networks can be a solution to the bandwidth issue and latency limitations. 5G is much faster and has a lot more throughput. Another solution can be using cloudlets, right? I mean, we talked about cloudlets. That can also help with the network bandwidth. Network availability is another concern. Constant and speedy internet connection must be ensured in mobile cloud computing. the mobile device is being always connected to the cloud anywhere, right? So for quality of service, you want to have a good connection and a lot of network availability so the users can use all the applications. Also, the security concerns, right? The advancement in technology has also brought new security risks within it. Everyone wants the protection of his or her data and is curious about it. In mobile cloud computing, the security issues have two aspects, one in mobile device security and the other in the cloud security. So not only are you dealing with the security on the device, you're also dealing with security on the cloud, right? So all of the stuff that you had issues with the cloud, you inherit with the mobile cloud. So, okay. And so, in conclusion, I covered mobile device technologies. I went over what cloud computing was versus mobile cloud computing. I also talked about some mobile cloud computing solutions, some offloading methods, cost-benefit analysis. Went over some examples. Talked about security and some issues. And that's it. And here are my references. I have 2 slides of references, so I'm going to show the next slide too. And I hope you enjoyed. It's an interesting topic, and I look forward to doing more research on it. Thank you.